Voyager 1, the most distant human-made object in the universe, is once again sending usable information to Earth. This remarkable spacecraft, the farthest man-made interstellar object in outer space, has already uncovered stunning discoveries, such as the secrets behind Jupiter's rings and the unexpected behavior of the heliopause. Now, after an incredible 45 years of exploring space, Voyager 1 is transmitting signals that could reshape our understanding of the solar system. These astonishing findings include strange ripples in the heliosphere, revealing how dynamic and turbulent this region is, vastly different from scientists' initial beliefs. Interestingly, Voyager's systems are behaving unusually. While it continues to operate, some of the data it transmits back doesn't make sense. How is the spacecraft still functioning, despite showing signs of malfunction? Could this indicate encounters with phenomena we didn't anticipate? Or are these hints of alien life or revelations of new cosmic mysteries? Join us as we delve into Voyager 1's incredible discoveries that have surprised scientists and explore what they could mean for the history of the universe. The history of Voyager 1, a journey beyond the solar system. NASA launched Voyager 1 on September 5, 1977, marking the beginning of one of the most ambitious space missions in human history. Along with its twin, Voyager 2, it was designed to explore the outer planets of our solar system, Jupiter and Saturn, and then continue onward into the unknown regions of space. Its primary mission was to collect and transmit data about these planets, their moons, rings, and magnetic fields, while also providing close-up images of the gas giants. However, no one could have predicted just how far Voyager 1 would travel or the groundbreaking discoveries it would make along the way. Voyager 1 was equipped with a suite of sophisticated instruments to measure various phenomena in space. Its payload included an imaging system for capturing pictures of Jupiter, Saturn, and their moons, a magnetometer to measure magnetic fields, a plasma detector to analyze the density and temperature of charged particles, a cosmic ray detector to study cosmic radiation, and a radio science system for detailed atmospheric and ring data. The spacecraft's trajectory was carefully planned to utilize gravity assists from Jupiter and Saturn, a technique allowing it to gather speed without additional fuel by essentially slingshotting around the planets. This enabled Voyager 1 to travel farther than any previous spacecraft, while continuously sending an unprecedented wealth of data back to Earth. Voyager 1's closest approach to Jupiter occurred on March 5, 1979, just 18 months after its launch. During this encounter, humanity received its first ever detailed images of the solar system's largest planet. One of the most remarkable revelations was Jupiter's rings, previously unknown. Until then, scientists believed only Saturn had a ring system. Voyager 1 demonstrated that Jupiter also possessed faint rings composed mostly of tiny dust or tiny d, a discovery that redefined our understanding of gas giants. The spacecraft also captured detailed images of Jupiter's Great Red Spot, a massive storm larger than Earth that has raged for at least 4 centuries. These images revealed strong winds swirling in opposite directions around the storm's center, with wind speeds exceeding 400 mph, making it one of the most powerful weather systems ever observed. Voyager 1 further documented smaller storms, lightning, and auroras on Jupiter, uncovering surprising parallels between its atmospheric dynamics and those of Earth. Another groundbreaking discovery was the observation of Io, one of Jupiter's moons, as the most geologically active body in the solar system. Voyager 1 observed volcanoes on Io erupting sulfur and sulfur dioxide hundreds of miles into space, marking the first observation of active volcanism on another celestial body. Scientists concluded that Io's interior was heated by tidal forces from Jupiter's immense gravity. Voyager 1's flyby of Saturn on November 12, 1980, marked another milestone. It provided the first detailed close-up images of Saturn's ring system, which were revealed to be far more complex than previously imagined. Instead of a single continuous structure, Saturn's rings consist of countless particles, ranging in size from tiny dust grains to boulders several meters across, orbiting in intricate patterns influenced by gravitational interactions with Saturn's moons. Voyager 1 also made significant discoveries about Titan, Saturn's largest moon, which has a dense atmosphere primarily composed of nitrogen with traces of methane and hydrocarbons. Though the thick haze around Titan prevented clear surface images, This discovery highlighted its similarity to the early atmosphere of Earth. Voyager 1 also identified new moons, such as Prometheus and Pandora, which help maintain the structure of Saturn's rings through gravitational effects. The mission's longevity and legacy. Originally expected to last just 5 years, Voyager 1 has continued operating for over 45 years, thanks to its durable components and NASA's ingenuity. Powered by radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium-238 into electricity, the spacecraft has maintained functionality by shutting down non-essential systems and activating backup components. In 2017, NASA successfully reactivated thrusters that had been dormant since 1980, underscoring the spacecraft's resilience. The latest mystery: signals from interstellar space. In May 2022, NASA announced that Voyager 1, now over 14 billion miles from Earth, began transmitting puzzling data from its attitude articulation and control system AX. This vital system keeps Voyager's high-gain antenna pointed at Earth. Although the AX indicated it was in an impossible orientation, Voyager 1 continued receiving commands, executing them correctly, and transmitting data. This paradox has left scientists questioning how the system can malfunction while the spacecraft remains operational. Suzanne Dodd, project manager for Voyager 1, noted that these signals pose a profound mystery. What could these inexplicable signals from interstellar space reveal? Are they signs of something far more mysterious than we have ever imagined? The Voyager 1 mission, an enduring symbol of human curiosity and ingenuity, continues to expand the boundaries of our knowledge, uncovering the universe's secrets one signal at a time. Its twin Voyager 1 at NASA's Jet Propulsion Laboratory, JPL, encountered a mysterious situation that sparked intrigue. This is somewhat expected at this stage of the Voyager mission. Now in interstellar space, the spacecraft is exposed to unprecedented levels of cosmic radiation, as no spacecraft has ventured this far before. Suzanne Dodd explained, "We're in a high radiation environment that no spacecraft has flown in before, raising the possibility that radiation could be affecting Voyager systems in ways not fully understood." The malfunction in the attitude articulation and control system, AX, presented a conundrum. While the telemetry data from the system was essentially useless, Voyager 1 had not triggered its safe mode. Safe mode is a protective state where the spacecraft powers down non-essential systems to allow engineers to diagnose and resolve issues. The absence of this trigger indicated that the spacecraft did not recognize the AX data as faulty. This added to the mystery. Complicating matters was the immense distance between the spacecraft and Earth, more than 142 billion miles, about 23 billion kilometers. Signals sent from NASA's Deep Space Network, DSN, take approximately 20 hours and 33 minutes to reach Voyager 1, and responses take just as long. This means every communication involves a delay of over 41 hours, creating a painstakingly slow troubleshooting process. Engineers must wait nearly 2 days to receive data after sending each command. Despite this delay, NASA engineers embarked on diagnosing the issue. Their first step was determining whether the problem was isolated to the AX or involved other systems. As part of the investigation, commands were sent to reboot the AX and execute various diagnostic routines to pinpoint the source of the corrupted telemetry data. One theory proposed by the engineering team suggested that the AX might be affected by cosmic radiation in the interstellar medium Mycelium on the heliosphere, where Voyager 1 has been traveling since 2012. This area is filled with charged particles from exploded stars, known as supernovae, creating a high radiation environment. The spacecraft systems, operating in uncharted territory, may be experiencing issues from prolonged exposure to this intense radiation. Additionally, Voyager 1 systems were designed to last only 5 years, yet they have far outlived their expected lifespan. To conserve energy, NASA has gradually turned off various non-essential systems and scientific instruments aboard Voyager 1. However, the AX remains critical. By 2025, Voyager's power levels are expected to drop further, forcing NASA to make additional cuts to maintain operation. Still, this power reduction does not appear to be the cause of the AX malfunction, as all systems are receiving sufficient energy to operate. Suzanne Dodd remained cautiously optimistic, stating, "I think if there's a way to solve this issue with the axe, our team will find it." One perplexing aspect of the issue is that, despite the invalid axe telemetry, Voyager 1's high-gain antenna remains correctly pointed toward Earth. The strong signal indicates the spacecraft is still properly oriented, suggesting the problem may not lie within the axe itself, but could involve interference from another system. Another potential explanation involves memory corruption caused by cosmic rays. These high-energy particles, originating outside the solar system, can penetrate spacecraft electronics and cause data corruption. Now, in interstellar space, Voyager 1 is exposed to more cosmic rays than it was within the protective bubble of the heliosphere, increasing the likelihood of radiation-induced malfunctions. As of March 2024, NASA had not pinpointed the exact cause of the axe malfunction. However, the investigation was ongoing, and engineers remained hopeful for a solution. Meanwhile, Voyager 1 continues transmitting valuable scientific data, expanding humanity's understanding of the cosmos beyond the solar system's boundaries. But what if these strange signals are just the beginning? What new mysteries might Voyager 1 uncover as it probes the ever-shifting boundary between our solar system and the uncharted depths of interstellar space? Ripples in the heliosphere. The heliopause marks the solar system's outermost boundary, where the solar wind-charged particles emitted by the sun collides with the interstellar medium. Essentially, the heliopause is a protective bubble created by the sun's magnetic field, encasing the solar system. Within this bubble, known as the heliosphere, the solar wind dominates. Beyond it lies interstellar space, where the sun's influence weakens and galactic forces take over. Voyager 1 was the first spacecraft to breach this boundary, entering interstellar space on August 25, 2012, after traveling over 11 billion miles from Earth. This monumental achievement marked the first time a human-made object left the solar system. As Voyager 1 ventured farther into interstellar space, it began detecting unexpected phenomena at the heliopause, surprising scientists on Earth. One of the most significant discoveries was the detection of ripples in the heliopause. These ripples suggest that the boundary between the heliosphere and interstellar space is not smooth or static, as once thought, but dynamic and fluctuating. The heliopause, once considered a stable barrier, is now understood to be influenced by external forces like shock waves from distant supernova explosions. These waves send powerful bursts of energy through the interstellar medium, which then interact with the heliosphere. When these waves collide with the heliopause, they create ripples detectable by Voyager 1's instruments. Voyager 1's plasma wave instrument played a critical role in identifying these ripples. Plasma waves are fluctuations in the density and movement of charged particles, which can be used to map the structure of the heliopause and beyond. In 2014, data from Voyager 1 revealed the spacecraft had passed through several ripple events, providing concrete evidence of the heliopause's dynamic nature. The timing of these detections, between 2012 and 2014, coincided with shock waves traveling through the interstellar medium, disturbing the heliosphere's edge and causing it to ripple. This discovery has profound implications. The heliosphere, once thought to be a simple bubble, is constantly interacting with the surrounding interstellar environment. The sun's magnetic field, extending beyond Pluto's orbit, is insufficient to completely isolate the solar system from the galaxy. Instead, the heliopause acts as a semi-permeable membrane, allowing particles and energy from interstellar space to pass through. This interaction can affect planetary atmospheres, including Earth's, as ripples in the heliopause influence the influx of cosmic rays. Furthermore, the discovery opens new avenues for understanding interstellar space, which is now known to be a turbulent and dynamic region. Voyager 1's data suggests that the interstellar medium is more complex than previously believed, with varying density, temperature, and magnetic strength. Scientists are exploring the possibility that the heliosphere has a tail extending beyond the heliopause, shaped by the sun's movement through the galaxy and interactions between the solar wind and interstellar forces. The interstellar medium is another critical aspect of Voyager 1's discoveries. It has revealed that the sun's activity, including solar flares and coronal mass ejections, causes the heliosphere to expand and contract, altering the position of the heliopause. NASA is currently planning future missions to explore these regions in greater detail. including the Interstellar Mapping and Acceleration Probe, IMAP, which is scheduled for launch in 2045. IMAP will build on Voyager 1's discoveries, providing more detailed measurements of the heliopause and the surrounding interstellar medium. If Voyager 1 could reveal the heliopause's shifting nature, what other hidden forces might be at play in navigating the immense gravitational pulls of giant planets like Jupiter and Saturn? Planetary gravitational forces. A common question about Voyager 1 is how this small spacecraft avoided being pulled into the massive gravitational forces of planets like Jupiter and Saturn. Voyager 1's journey through the solar system involved flybys of some of the most massive planets, particularly Jupiter and Saturn, whose gravitational fields are immensely powerful. Jupiter, the largest planet in the solar system, has a mass over 317 times that of Earth and exerts a strong gravitational influence on its many moons and the asteroid belt. Similarly, Saturn, with its iconic rings, possesses a gravitational field capable of trapping spacecraft passing nearby. The key to Voyager 1's successful journey lies in the use of a technique called the gravitational slingshot, or gravity assist. This maneuver uses the gravitational pull of a planet to accelerate a spacecraft and alter its trajectory without additional fuel. Although counterintuitive, this technique works by carefully calculating the spacecraft's trajectory so that it passes by a planet at just the right angle. As Voyager 1 approached Jupiter, it was pulled in by the planet's gravity. However, instead of being trapped, its trajectory was designed so that it would accelerate as it slingshotted past. By the time it exited Jupiter's gravitational field, Voyager 1 was traveling significantly faster than when it entered. During its flyby of Jupiter on March 5, 1979, Voyager 1 increased its velocity from approximately 35,000 mph to over 43,000 mph using this maneuver. This increase in speed was crucial for propelling it towards Saturn. A similar gravity assist was executed at Saturn on November 12, 1980. Careful calculations ensured Voyager 1 passed close enough to gain speed without being pulled into Saturn's gravitational well. These maneuvers allowed Voyager 1 to escape both planets' gravitational pulls and continue its interstellar mission. Voyager 1's trajectory was meticulously planned by NASA engineers, who spent years calculating the exact paths required to take advantage of gravitational forces. This involved predicting the planets' positions, their motions, the influence of their moons, and their magnetic fields. The timing of Voyager 1's launch was no accident. It coincided with a rare planetary alignment, known as the Grand Tour Opportunity, which occurs only once every 175 years. This alignment allowed Voyager 1 to visit Jupiter and Saturn using gravitational assists and continue into interstellar space without excessive fuel. Without this precise timing, Voyager 1 would not have traveled as far as it has today. The Golden Record. Voyager 1 is a time capsule. One of the most unique aspects of the Voyager 1 mission is its role as a time capsule for humanity. On board the spacecraft is the Golden Record, a copper disc coated with gold intended to communicate with any alien civilizations that may encounter Voyager in the distant future. This record contains a curated selection of sounds and images representing life on Earth at the time of Voyager's launch in 1977. Designed by a team led by Carl Sagan, the record includes 115 images, natural sounds such as wind and thunder, music from diverse cultures, and spoken greetings in 55 languages. These elements were chosen to showcase Earth's cultural and biological diversity, as well as basic scientific information about our planet. Musical selections include works by Johann Sebastian Bach, Ludwig van Beethoven, and a traditional song from Peru. The Golden Record symbolizes humanity's desire to communicate and share knowledge with the universe. Although the chances of another civilization finding and understanding it are slim, its inclusion demonstrates the human drive to explore. Some have speculated humorously about aliens already interacting with Voyager, highlighting its potential role as humanity's ambassador in space. Voyager 1 is currently traveling at 38,000 mph and will take about 73,000 years to approach the nearest star system, Proxima Centauri. If an alien civilization encounters it, the Golden Record's contents could provide insights into Earth's geography, human anatomy, and scientific concepts like DNA and the solar system's structure. Greetings in 55 languages further emphasize Earth's rich cultural diversity. As Voyager 1 continues its silent journey through interstellar space, it carries humanity's hopes, questions, and a snapshot of our existence. The spacecraft's discoveries may reshape our understanding of interstellar travel and space itself. What other secrets might it uncover in the vast cosmos? Share your thoughts and speculations about Voyager 1's mission and its potential future revelations.